In this video, we're going to look at a very important limit that you will need going forward. This limit is one that is proven using the squeezing theorem that we looked at in the last video. And it says that the limit of sine of theta over theta as theta tends to 0 is 1. Now, if you substitute 0 in for theta, you'll get sine of 0 over 0, and sine of 0 is 0. So it's 0 over 0. It is that indeterminate form that we talked about previously. So what we're going to look at in this video is a proof of this limit. And so what we're going to need to do in order to use the squeezing theorem is to trap this function sine of theta divided by theta between two other functions, and we're going to use a geometric construction to come up with our functions. Alright, so before we do that, let's start off with the following supposition. We are interested in values of theta that are close to 0, so let's say that we're going to work with a value of theta that is smaller than pi over 2. That'll place the angle in the first quadrant when it's in standard position. And implicit in what I just said is the further supposition that the angle is positive. So the angle is between 0 and pi over 2. Now for negative angles, you could come up with a very similar proof. But anyway, let's consider the unit circle. Alright, so what we have here is the unit circle. That's the circle centered at the origin with radius 1. And so I've drawn a line segment from the origin out to some point in the first quadrant. Let's call this angle theta, the angle that the line segment makes with the positive x-axis. Now, the point where the line segment intersects the unit circle we'll call point B. The point where the circle intersects the positive x-axis we'll call C. If we drop a vertical line segment down from point B until it reaches the x-axis, the point where it intersects the x-axis we'll call A. And then if we extend a vertical line segment up from point C, the point where that line segment hits our original line segment we'll call D. So what we're going to look at are two triangles, two right triangles, and a circular sector. So we're going to look at this right triangle from O to A to B. O is the center of the unit circle, the origin if you will. And then we're also going to look at this right triangle OCD. Clearly the area of angle OCD is bigger than the area of triangle OAB. Now, there is also what we call a circular sector that we're going to look at. What is this circular sector? Well, it is the circular sector OCB. So it includes all of the triangle OAB plus this little sliver with vertices A, C, and B. So I think it's clear that the area of this smaller right triangle is smaller than the area of the circular sector, and the area of the circular sector is smaller than the right triangle OCD. So what we're going to do is come up with expressions for each of these three figures, for the areas of each of these three figures. Alright, so let's start working with the triangles first. You know that the area of a triangle is half the base length times the height. And one other fact we're going to need is that on a unit circle, if you've got a line segment that extends from the center through the circle, that the coordinates of that point where the line segment intersects the circle are cosine theta for x and sine theta for y. And again, theta is the angle made that the line segment makes with the positive right axis. So the coordinates of point B are cosine theta and sine theta. Alright, so the area of triangle OAB is going to be 1/2 the base times the height. Well, the base is just the x-coordinate, and the height is the y-coordinate. So we get that the area of triangle OAB is 1/2 cosine theta sine theta. Now let's go on to the circular sector OCB. It is a well-known fact from geometry that the area of a sector with angle theta is going to be one-half r squared theta. Well, in our case, we're talking about the unit circle, so r is 1. And so the area is going to be just 1/2 theta. So far, we have 1/2 cosine theta sine theta is less than 1/2 theta. Now let's consider the area of the right triangle OCD. Well, one thing I want to observe is that the length of line segment CD is tangent theta. How do we know that? Well, if you remember the definition of the tangent of theta in terms of the sides of a right triangle, the tangent of theta is equal to the length of the opposite side divided by the length of the adjacent side. So the tangent of theta is going to be the length of DC divided by the length of OC. However, the length of OC is 1. So the tangent of theta is the length of CD over the length of OC. This is 1, and so it's just the length CD. Alright, so we've got tangent of theta for the height of the triangle OCD. Its base is 1, and so the area of triangle OCD, yes, is 1/2. The base is 1, and the height is DC, or tangent theta, and this is the area of triangle OCD. And the area of triangle OCD is bigger than the area of that circular sector, so we get this 3-part inequality. 1/2 cosine theta sine theta is less than or equal to 1/2 theta, is less than or equal to 1/2 tangent theta. Let's now see how we can manipulate this inequality to arrive at another inequality which is useful to us. So starting with this inequality, we multiply each part of the inequality by 2, and that gives us the cosine of theta times the sine of theta is less than or equal to theta, which is less than or equal to the tangent of theta, which I've rewritten here as sine theta over cosine theta. Now we're going to multiply, or rather divide, each side by the sine of theta. And since we're in the first quadrant, the sine of theta is positive, and we're going to be dividing by a positive amount, and that means we don't have to worry about changing directions on the inequalities. So if we divide each of the 3 parts by sine of theta, we get cosine of theta is less than or equal to theta divided by sine of theta is less than or equal to cosine of theta. I hope that middle part is looking familiar. So now we take the reciprocals of all 3 parts, and when you take reciprocals, the directions of the inequalities change. So we're going to get 1 over cosine theta is greater than or equal to sine of theta over theta, which is greater than or equal to cosine of theta. Now, what we have is the function that we're interested in trapped between 2 other functions. And look at what happens when we take the limit as theta tends to 0. Remember that the cosine of 0 is 1. So that gives us, since the limit of the left part of this inequality as theta tends to 0 is 1, and the limit of the right part is the same, by the squeeze theorem, the limit of sine theta over theta as theta tends to 0 is also 1.